Hello and welcome back to another video where I actually did my hair for this video, so I'm not wearing headphones. So today we'll be tackling a problem that might seem a little tricky from the outset, but is actually more than fine. There's only one other axiom that we need for this problem. Everything else we already know. It just takes a bit of creativity. So let's get right into the video. So first things first, I'm not going to read them again, but these are our 5 assumptions again, which I'm sure by now that we're familiar with. And additionally, we have the continuity principle, where if we have 2 overlapping circles, then we are assured by this principle that they must intersect at 2 points. And finally, we know how to construct an equilateral triangle, so I'll just do that quickly. Line segment between 2 points, axiom 1, circle, circle using axioms 3 twice. From the continuity principle, we have that this is an intersection. And finally, using axiom 1 again, we can just connect these dots, and then with the magic of technology, we can remove those construction circles to give us an equilateral triangle. And then using the distance or length thing, this just proves that's an equilateral triangle, in case you were wondering. I figured out how to use it. Okay, so now we are at the very crux of this video. The problem we are given is, given any 3 distinct points, A, B and C, is it possible to construct a circle with center point as A and a radius equal to BC? When I first thought of this problem, I thought it would be incredibly nice if those 3 distinct points were just so happening to be on an equilateral triangle if you connected up the lines, because then that gives you what you want. The only problem with that is that's a very specific situation and it does not specify that in the question. So we need to be a little bit more general with our solution here. Okay, so to do this problem, what I will do is somewhat arbitrarily place 3 points like that. Okay, so what can we use here? These are our points A, B, C. So what can we use? What do we know? We know that we can make a line segment between A and B, and then doing the typical construction for an equilateral triangle, it gives us this. And I will just hide the construction marks because I don't want to make this more confusing than it strictly has to be. And additionally, what I'm going to do, just to really show off what's happening here, I am going to move C to here. That's not because it doesn't work, it's just because I'm just trying to highlight what's happening here. And with it being in line with B and D, that makes it a little more difficult to see. Okay, so now the point that we're interested in, this line segment B and C, we know we can do this because of axiom 1. This is the length that we're interested in, and it doesn't seem entirely obvious at the minute how we can construct a circle with center A that has this exact radius. We don't know any lengths here, so what do? Is because we know that circles and straight lines exist, I'll use center B to make a circle, which we know we can do with axiom 3. Now I've got a circle with radius BC, and now we have reached a bit of a problem. So what I'm going to do is give you another axiom. Okay, so we have the circle line or circle line segment continuity principle. Here it is explained explicitly as it is in the literature. The main essence is that if a line segment, and this therefore extends to lines as well, has one point inside a circle and another point outside of a circle, then we can say the point at which it crosses is its intersection, and that point is F here. Now, line segments are guaranteed, if there is an intersection point, to intersect at least once and at most twice, whereas a line will intersect exactly 2 times. Okay, so back to our construction. Why is that principle exactly needed? Well, it's needed for the same reason as the circle-circle continuity principle. It's not exactly clear within what space we're working with here. We could be working in a space very similarly to that of the rational numbers, where there is plenty of gaps, and so it actually might just slip through the cracks of the circle. But what the continuity principles in essence say is that there are no gaps in the space of circles and lines, and that in a very similar sense it's synonymous with that of the real numbers, in that there is no gaps in these structures, which assures us that these intersection points actually do exist, which is why we can claim that point C is on the circumference of this circle, which is necessary. Now, if you've taken a slightly different set of points A, B, and C and made your equilateral triangle, it could be the case where your point D and B, this line, could already intersect the circle. But in this case it doesn't. But regardless of what you want to do, if it doesn't, then what we want to do is extend in either direction, this way or this way. We just want to extend the line segment down so that it does intersect. So along this, so your point E, if this line segment does intersect this circle, then your point E will be between points D and B. If it doesn't, you need to make an extension, and then it will be on side B or side D. It doesn't matter. We just need this additional intersection. Okay, so I've just zoomed out a bit, because what we're doing next is using this point D as a center point for this next circle. We want its radius to be equal to DE. That's its radius. Okay? So now we have a new circle. Okay, so what we want to do now is additionally extend this line segment DA to meet this new outer circle at point F. Okay, so what we've got now is that we are really, really close, but I need to do some explaining first. So first things first is that we notice that D to E is equal to D to F. Okay, these are just the length of the radius of this circle. And we know that this is an equilateral triangle. It's the one that we constructed earlier. So we know the length of D to F minus the length of D to A is equal to the length of A to F. Okay, and if you don't believe me, GeoGebra is telling me this is 3.4, whatever that means, how many units. Okay, similarly, the length of D to E minus the length of D to B is not only the length from D to E, but is equal to that of A to F, 3.4 again. And finally, we notice that B to C is this circle's radius as well. So that's 3.4. So now, finally, to answer the question, with center point A, is it possible to make a circle with a radius of length B to C? All we need to do now is make a circle from A to this point F, and then I will hide all of these additional construction marks, and there we have it. That's our circle with the exact length that we want. Right, and that's the video. It's one of those problems which requires a bit of creativity, and that's always the case with mathematics. It requires a lot of little steps, and if you don't know those steps, it can seem like one massive one. But I promise you, I tried breaking it down as much as I could in this video, of all the steps I was taking, when I was using what axioms, why, and my general thought process over the entire video. Hopefully that was helpful in terms of thinking about how these axioms can be used to solve all sorts of problems, even in problems where you want to make a circle of a certain length radius. And that's all for the video. Thank you very much. Remember to hit that like button, comment, subscribe, and I'll see you later, you fucking nerds.